Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com, and today we're going to be looking at computing limits at infinity and end behavior. That is, we want to talk about how functions behave as the independent variable increases or decreases without bound. What happens as x goes to infinity? What happens as x goes to minus infinity? If you like this video, feel free to click the like button. You can also comment in the comment section, and you can share this video with your friends and classmates if you find it would be helpful to them. There are worksheets available also in the comment section of the intro video, including this one. Let's try this first problem. It reads, find the limit for the following. And we have the limit as x goes to infinity of a rational function. Well, because the degree of the numerator is larger than the degree of the denominator, we look at the division of the leading coefficients, seeing that it's positive, and this tells us we go to positive infinity. So a good way to answer this question might be to write the positive infinity symbol. Alternatively, DNE can also be written, as in does not exist. Anytime a limit is not a real number, we can write this, DNE is okay too. In this next problem, we're taking the limit as x goes to positive infinity of a cubed root of a rational function. So this is a composition function. With compositions involving roots, we can often pass the limit inside the root. This is done provided that the limit of the radicand, the quantity inside the root, actually exists, and I believe it does here. So we'll go ahead and write this as a cubed root of the limit of this expression as x goes to positive infinity. And I believe in this case, we can evaluate that limit without too much difficulty. It is, after all, just a rational function where the degree of the numerator and the degree of the denominator are the same. So let's take a look at it. Because the degree of the numerator and the degree of the denominator are the same, we can observe the ratio of the leading coefficients and the limits of a rational function as x goes to plus or minus infinity. When the degree of the numerator and denominator are the same, that's going to be equal to just the ratio of these leading coefficients, which is 5 divided by 7. So hence, this is 5/7. And it follows then that the value of the original expression is the cube root of 5/7. I'm going to be a little bit careful about applying this rule, namely of passing a limit inside a root. It only applies when the limit of the radicand exists. And for the next problem, we'll go ahead and observe that this is just a straight rational function, limit as x goes to infinity. So we can go ahead and right off the bat, just take the ratio of the leading coefficients, which is going to be 3 over a1. Hence, the value for this limit is going to be just 3. Now, there is a connection between the limits for rational functions and horizontal asymptotes. Aside, it so happens that y equal to 3 is the horizontal asymptote for this function. So we have that the graph is hugging its horizontal asymptote in these cases as x goes to plus or minus infinity. So this is the horizontal asymptote for this function. Let's try this next problem. We have the limit as x goes to minus infinity of a tricky looking quotient function. For this type of problem, we may try the technique of multiplying numerator and denominator by what would be reciprocal powers of x. I think in this case, we might want to use 1 over the absolute value of x in the top and in the bottom. So notice that as x goes to minus infinity, the numerator is actually going to minus infinity. If you mistakenly use 1 over x, we're inclined to make some sort of sign error. So it's better to use absolute value of x here. aside, we have that absolute value of x has two looks. It is equal to either x or negative x, and this would be when x is greater than or equal to 0, whereas it's negative x when x is negative. We also have that the square root of x squared is equal to absolute value of x. So taking this all together, I think what we can do is in the numerator, we'll replace the absolute value of x by negative x. Since x is going to minus infinity, we really would be having this look in the numerator. And this gives us the following. So we're going to have 12x plus 7 over negative x. We got then a big division bar. And under the division bar is the root expression. And this root expression has yet another division bar within it. So this is what that will look like when we simplify and use the fact that absolute value of x in the numerator is behaving like minus x. You can see that we can further simplify now. So we get the limit as x goes to minus infinity. In the top, it is negative 12 minus 7 over x. And in the bottom, we have that property of roots that a quotient of two square roots is the square root of the quotient of the radicands. So that means I can write a single root, and inside we'll divide what is x squared into the numerator, which is going to be 36 minus 15 over x squared. I think at this point, we can see that the limit can be applied. There are a couple transient terms. So transient means that the terms go to 0 in the given limits. So that term right there and this term right here are transient. The rules for limits tell us that a limit of a quotient can be obtained by applying the limit to numerator and denominator, provided that the individual limits exist and the denominator limit is not 0. So what we're doing is we're applying the limit to the top, we're applying the limit to the bottom, and then we're passing the limit inside the root, which we know we can do provided that the limit of the radicand exists and the root exists. And in this case, it all is working out. We find in the top just minus 12 after applying the limit. And in the bottom, passing the limit inside the root, applying it to the transient term, we get 0. So it's just the square root of 36, which is a 6. Our final answer then for this one is going to be a negative 2. A little bit tricky, but we managed to get it. Let's try the next one. So in the next problem, we want to take the limit as x goes to infinity of an interesting difference function. So the first term in the difference is going to infinity, whereas the second term is going to minus infinity. So who's going to win that race? I think in this case, we can try multiplying by the conjugate. So we'll go ahead and put this expression over 1 and multiply by x squared plus the square root of x to the 4th plus 10. And we'll do the same in the bottom. So that 1 is also going to be multiplied by this conjugate. Seems like the right idea. Sometimes, your spider sense in calculus just tells you, use the conjugate. I believe this is going to be working out. So in the top, we have what is x to the 4th. Now simplifying, we find in the numerator using FOIL multiplication technique, x to the 4th. Also, the outside and inside products appear to be opposites, so that's nice. They will cancel, and that means we're just left with minus what is the root expression times itself, which will be just that quantity inside the root. Make sure to use parentheses here because that minus should distribute across to the two terms, x to the 4th plus 10. In the bottom, we have still this conjugate root expression. x squared plus the square root of x to the fourth plus 10. And the next thing to do now is to see if we have any simplification. Well, looks like we do actually. In the numerator, the x to the fourths are canceling. Let's not forget also that there's still a limit here as well. It's a big blunder to forget to write the limit. So we patched it. We have the limit as x goes to infinity of just a minus 10 in the top. And in the bottom, there is an expression which clearly is going to infinity. Well, this limit, does it exist or not? Yes, it does. So when the numerator is a constant and the denominator tends to infinity, we say the limit is 0. Let's try the next one. So here we want the limit as x goes to infinity of 3 plus e to the x squared. We know exponential e to the x blows up to infinity as x goes to infinity. So e to the x squared will also go to infinity. The plus 3 is kind of immaterial here. We can say that this is equal to infinity. Also, dne is a suitable way to answer this question, as in the limit does not exist. Infinity, in a way, though, is a little more telling. It's saying not only are you not getting a real number, your function values are blowing up to infinity. So it's a little more telling to use the infinity symbol. Now, what about this one? The limit as x goes to positive infinity of 3 plus e to the minus x squared. Well, e to the minus x squared is a sort of Gaussian function. Those of you that have studied statistics before, you've worked, no doubt, with this type of function. This is looking a lot like that standard normal distribution, right? The standard normal distribution is just a normalized Gaussian function. So this could be your e to the minus x squared. There is an asymptote, which is the x-axis, and the function from both directions, it actually approaches this asymptote. Let's see if we can draw it nice. So here, the asymptote would be like the x-axis, and it would be the case that the y values are coming down to that value where y is 0 from above. You never reach y is 0 with this function, but you can get as close as desired by just taking x large enough positive or large enough negative. In this case, as x goes to infinity, the function values tend to 0 for the Gaussian function. And so we're just going to get here what is the value 3. So this is equal to 3. And our final function to study, maybe we'll use a graphing calculator to assist us. So we want to graph the inverse tangent function to get a look as to what the tan inverse of pi minus x cubed might be. Well, I suppose we could go ahead and graph just the standard inverse tangent function. So we have second tan inverse of just variable x here, just to get a look at it. So you remember, you get this function by taking what is one period of a stock tangent function, the period between minus pi over 2 and pi over 2, and then reflecting that across the line y is equal to x. So you get this graph. The question is, what happens if you replace the argument by pi minus x cubed and you let x go to positive infinity? I like to think of it a different way. As x goes to positive infinity, you can see that the argument is going to minus infinity due to this minus x cubed. The pi is really immaterial here. So it's like we're asking the question, what happens is you let the argument of tan inverse of x go to minus infinity? Well, in this case, you are going to have your y values plateauing to what is a horizontal asymptote. The horizontal asymptote is going to be y is equal to minus pi over 2. And so we conclude this problem by stating to that effect that here the limit is equal to minus pi over 2. And with that, we've solved yet another worksheet, this one being on limits at infinity, limits involving infinity, and end behavior. If you like this video, feel free to click the like button. You can subscribe to the channel and follow my other videos on solving calculus through worksheets. Thanks and goodbye.